This is part 3 in a tutorial trilogy I'm making, but you don't need to have watched the other parts to follow along, they're all independent videos. Today's video is actually a little bit different than the others, because it's non-scripted, so you'll get to see my full thought process as I make this more advanced sorting visualizer. I do it this way because my other thought process video with the talking avatar is now the most successful video on my channel, by far. So I thought I'd try again. Anyway, unlike in the other two projects, in this one I go all out and make this crazy thing. There's an animated bird at the top, sorting the socks with its feet. The character and the socks are procedurally generated, so I'm not using any images at all. The socks have physics, which I think is a nice touch that emphasizes which swap was made without being too overwhelming, so you can still follow along what the algorithm is doing. The physics, character design, and animations are all done from scratch using just vanilla JavaScript, mathematics, and HTML canvas. To follow along, you just need a code editor and a browser to test. But if you do decide to follow along, prepare for some back and forth. There will be some mistakes, so bear with me as I try to sort things out. Get it? Sort things out? Because we're gonna... No. Gonna code, debug, and have fun. Coding with Radu. Coding with Radu. Gonna prototype and design. Coding with Radu. Coding with Radu. Let's code now. Alright. Let's get things started. Haven't felt creative in a while, but hope today will make things different. The visualizer that I have in mind, I got the idea from watching these robot animators. I'm gonna put some video on the screen right now so you know what I'm talking about. I mean animated robots that do the sorting, different algorithms. And today I'll focus on the bubble sort like in my other two tutorials. But I already have some idea in mind for the character. It's not gonna be a robot, it's gonna be a bird somehow sitting on top of a string or a bar or something. And then the bird is going to switch things around. And the things that are hanging from that are gonna be socks. Because I always find myself sorting socks when I do the laundry. So I like them to be hanging next to each other in pairs. And I like this idea. And I'm gonna try to do it today. I'm defining here a simple HTML page. I gave it the title of sorting visualizer and I'm linking a style sheet. I'll also link a JavaScript file in the body, but let's give this a title that is visible in the body as well. And I'm going to make the whole project pretty much on a canvas element. So let's define here a canvas with ID my canvas like this and include the JavaScript file as well. We need to create these. Let me just close these tags. All right. So I'm coding this without prior tries. I did do the other visualizers before, the simpler ones, so I have some kind of idea of how this will go, but you will see the full thought process kind of like in the avatar video. So let me define here the style.css file and the script.js file. Probably will gonna use a lot of scripts because this is a relatively complex project what we are building today. Yeah, so let's say that we are sorting a fixed number of elements. I'm going to define here n is equal to 20 elements and we will store these in an array. I'm going to randomize this array. So, I mean, put random elements in this array. Like that. And I'm going to put these just random values between 0 and 1 using this math.random function. It's how it works. Now, let's see if this works. I'm going to log this in the console and refresh the page. Yeah, we get the title of sorting visualizer here, and the array, 20 different elements, all of them are between 0 and 1. They are appearing here. And I'm going to continue a little bit like in the second sorting visualizer I made, the one with the columns. Because I liked the way I did the animation there, the way I structured the code. And I think that I'm going to use that for the character animation as well. Of course, things will get more complex afterwards, but I will begin in this way and see where it goes. So instead of working with columns this time, I'm just going to call them socks, since I know that these are going to be socks now. Let's say socks is equal to an empty array, and I'm gonna have them evenly spaced somehow on the string. So let's say spacing is equal to the size of the canvas width divided by n. So I want to put them spread apart depending on the size of the canvas. I will do here my canvas dot width divided by n, like so. And now let's get the context to draw on the canvas. So my canvas get context 2D, the 2D drawing canvas. It's going to be a 2D animation. And I'm going to need to define a class for the socks. Let me create a new file, sock.js, and include it here as well, sock.js. And the class is going to look like this. Class sock. And the constructor, I want to define this sock at some specific XY location, and that will be where it's hanging. So the middle of the sock where it's hanging, and then I'm going to give this sock a height. So I want to know how long it is. And I'm going to do this like so, x, y, and height. I think the socks are also going to have some kind of width, but all of them are going to be the same. So let me just define it here, a fixed width, maybe something like this dot width is equal to 10. And then let's store the other parameters there as attributes. So x is equal to x, this dot y is equal to y, and this dot height is equal to height. And we will like to draw this somehow. So I'm going to draw it as a simple rectangle. Sorry. On the canvas context. And I would like to have the left part. It would be good to have some helper variables here. So x is going to be the middle of the sock. Like if the sock is like this, then x is going to be here in the middle. I want to know the left part of the sock and the right part of the sock when doing the drawing, and these helper variables is good to define them. I did this in the other video as well. So this dot x, minus this dot width divided by 2. That's going to be the left. And same thing goes for right, but with the plus here. I don't think I'm going to need the right now, but yeah. And bottom is going to be this y plus this height. Yeah, and let's just draw a rectangle for now. So CTX begin path, CTX rectangle from the left top. So left, I already have it. The top is the y, so this dot y. And now the width and the height. So this width and this height. This is just a simple drawing that I'm doing here of a rectangle for now, and later we will style these as socks and probably add some physics. Let's see how it goes. Right, now back in the script, let's try to generate these socks. So I have already the array of random values, but I want to get socks with these properties, like lengths coming somehow from that. So I'm going to do for I is 0 to the size of the array. I'm going to need an x value for each of this sock. So I'm going to multiply this I with the spacing that I defined previously to get this x. I will also have to add half a spacing if I want these to align properly, but let's just keep it simple. So I just multiply I by the spacing, and later I will align them better. So let's see. And the y is going to be, maybe I'm going to put this in the middle of the canvas. So my canvas height divided by 2. So the string is going to be somehow in the middle of the canvas vertically. And this is where the things are going to be hanging from. And now the height of this sock is going to be equal to the maximum height should still fit in the canvas. So this value at most, but I'm going to leave a little bit of margin at the bottom. So I'm going to say times 0.4 instead of 0.0 instead of times 0.5, which is the same as this. So I'm going to have it less, and this value I will multiply it with whatever the array tells us. So the array here is a fractional number between 0 and 1, and I multiply that with this canvas height. So if the number is 1, then this maximum possible height of the sock will happen, and if the number would be 0, then this sock is invisible pretty much. But in between values are going to be scaled by this scalar value here. So let's just multiply this by the array of I, and now define the sock. So socks of I is equal to new sock using x, y, and the height, and draw it. Socks of I, draw on this canvas context. So I want to see now when I refresh the page. All right, something is working. So the canvas here is 300 pixels width and 150 pixels height. you can see the first hanging sock here. It's cut off by the side of the canvas straight in half. So this is what I meant, that I would like to add half this spacing here. So that now when we refresh, the first sock is aligned properly relative to the left side here, and the same goes for the last sock. Nice. I'm gonna think about these sizes a little bit later, because I don't really want to have socks that are so small, and I would like these to be actually pairs, so pairs have the same length and color maybe. I mean, yeah, this is gonna be a colorful application. But for now, I think I keep things simple. Let me structure this a little bit better so that I align things to center. So I'm going to put here display flex to the body and flex direction to column, so it's one below the other. And align items to center. So this style from here, I'm going to copy it to the body. Like this. And now every time I refresh, I see this happening. And my screen size here has a width of 500. So let me make the canvas. I will make it in JavaScript. Here at the top, I'm going to define the width and height of the canvas. I'm going to force it to be a specific width and height. .500 width. So now when I refresh, I get this full screen canvas here. Okay. And the height, I'm going to make this one a bit bigger as well. Now it's 150, I'm going to make it, say, 300. Yeah, this is good. I think I want the Y part where the socks are hanging from to be a little bit more up. So I'm going to put it, instead of times 0.5 here, times 0.4. And this will leave here enough room for the character. Maybe 0.45, a little bit lower. Yeah. And let's draw also this line where the socks are hanging from. So let me put here CTX move to. Okay, let's define this as the string location. So the vertical location of the string. Let's call it string height. Okay, and now we reuse this here. And I'm gonna draw that line. So CTX begin path, CTX move to 0 on the X and string height on the Y, and line to the width of the canvas. So I want it to span across the canvas, but the same height there. And then CTX stroke. So this part is drawing the string like so. And then from the string, we have hanging socks. All right, good. Now I'm going to style these a bit later, I think. But I would like to work a little bit on the positioning here. So I want to add some kind of margin here to the side of the screen. I don't want these socks to be so close to the side of the screen. The character is probably going to be cut in half, and I don't want that. So let me define here a margin. I'm going to say margin 30 pixels. And now here I'm going to add this margin. When defining the spacing, I'm going to consider this margin. So this needs to be above here. The available space is going to be my canvas width. Let's say here, available width. My canvas width minus two margins, one on the left and one on the right. Like this. So this is going to be available width divided by n. And here the x, it's not going to be offset by just half the spacing, but also by the margin like this. And I think, yeah, this is much nicer now. So these values here, the space here on the side is just what I wanted. Interesting. Okay, I'm thinking now if I would like this string to curve a little bit, but let's see how it goes, and if there is time at the end for such things, then it's fine. Otherwise, it's this rigid bar that we have, the character moving on. Okay, so I'm happy with this now. And what we need to do is start our animation loop. So I'm going to use the same technique that we used in the second tutorial, where we don't just animate the socks flipping, switching places in the swap phase of the bubble sort algorithm, but they transition from one location to another. And to do this, we use this technique I showed you there, where we have one single animation loop in the main frame, in the main file, and then each of the socks will generate their own keyframes in between. They will tween to different locations. So in this way, we don't have a secondary timer interval for each of the socks, which is another way that you can do this. But then the code becomes a little bit messy because you have to wait for some animation to end and detect that change and then start another. So here I'm just using one single animation loop, and I'm curious if I can do the character animation using this technique. So it's just an experiment pretty much. But yeah. So since I'm not going to be drawing these here anymore, this is the sock creation. Okay, happening here. Let me move also these other global variables up here. So now the array is initialized, the socks are created, and then drawing the string. And now I want this drawing of the string and of the socks. So to happen on each frame. So the ith sock draw on the context, the same thing that we had before here when defining the socks, but now I'm separating in the code into the part where we are creating the objects up here and drawing the objects down here. This will happen in an animation loop. So I'm going to call animate, and this function animate is going to do this drawing, the string and then the socks on each frame, and then we request animation frame, where we pass this animate function as a parameter. So this will call this animate function again and again and again as fast as it can, usually about 60 frames per second. But now if I'm going to leave it like this, it's gonna just draw on top of itself. It's like a canvas that a painter is drawing. It's drawing one thing and then again and again and again on top of it. We need to clear it before redrawing each frame. So I'm doing now ctx clear rect 0, 0 my canvas width, my canvas height, so the whole size of the canvas. Refresh, and everything still looks as before. But it is different because now we have redrawing happening on each frame. So if I'm going to go, for example, here in the sources inside of the animate function and put a breakpoint here, okay, why doesn't this work? This should clear it. Okay, for some reason this doesn't work. Let me try to reopen the console. Yeah, now it works. Sometimes the console can be buggy like that. So the line was drawn here, and now each sock is going to be drawn one by one. Until the end. And then when it's done, it's going to call that request animation frame, clear everything again. Why doesn't it work? It should clear the rectangle. I mean, the whole canvas. This is interesting. I don't know if it's a problem with the debugger or if it's something that I did wrong in my code, but clear rectangle. Let's try fill rect, or yeah, fill rect, and fill style set to white so that it redraws a white rectangle on top. I'm curious if this has an effect. Red. Okay. Hmm. I think there's just something wrong with the debugger. I'm going to undo this change. I think it works, but for some reason when debugging like that, it's not happening. If I uncomment this, if I comment this, then I can see these lines here appearing much thicker because the drawing on top of each other is happening. So I think it works. It's just something strange that's going on with debugging. So hope I can debug later things normally. Okay, so I want each of these socks to be able to be moved to some other locations. I'm going to go here in the sock class and define a move to method for it. And I want it to go to some location in a specific number of frames. So if that animation loop goes 60 frames per second, and I would like it to take about 1 second to go there, I should put here frame count is equal to 60. And that will mean that going to a new location is always going to take 1 second, pretty much. It's not exactly, but around that value. And I want to generate in between keyframes, like in between values of this X and Y during the move, and store these in a queue. I'm going to define here a queue, which is empty in the beginning, but every time we call this move to, we will add to this queue the 60 different in-between locations. So to the destination, from the current XY to the destination. So I'm gonna say, let's start at 1 because I don't want to animate to the current location that we are at. So you'll see what I mean in a second. Like this. Then I'm gonna use percent here. So let's get the fractional value between 0 and 1, like t is equal to I divided by the frame count. So this is going to be a number between 0 and 1. When I is exactly frame count, this becomes 1. And when I is 0, this would be 0, but it's not. It's going to be 1 divided by 60, which is very close to 0, because I'm going to interpolate between the current location and this new location. And this t is going to be giving me how far away from the current location to the new location I need to be at each frame, at each part inside of, at each position in this queue. Yeah, so I will basically say here this queue, push, and then interpolate. So I will have a function for linear interpolation. Let's call this VLERP, because V will stand for vector. We will do some linear algebra here. soon enough. Most definitely, because I want to do some physics as well. And it makes things much easier. So we interpolate two vectors between between xy here and the location xy. So I can just pass here this because I know that this is going to have an xy, or just put here, yeah, yeah, let's just put in here this. Wait a second. No, I don't like this. This position, this location, and new location is going to be the name of this. I want to change things a little bit. Bear with me. So I want to refactor so that here we store x and y in a location object with x and y like this. It's more natural, I think, to group these together, and it will help in future functions as well. So now I'm going to interpolate between this location and the new location, which will be in the same format, and using this t value to control how far we are along the path. Right, now I need to also change here x and y to be part of this location. So what I can do here is say x and y is equal to this location. I'm doing a destructuring assignment. And now I don't need this anymore. I actually get a shorter code here when I access x and y. Like this. I think it should still work. Yeah, so we are adding to this queue these using linear interpolation. I need to define this vlerp. And inside of this draw function, I'm going to have to modify the location if there are things in the queue. So if this queue has elements in it, I'm going to say this location is equal to this queue shift. I take the first element of the queue, assign it to this location. That's it. Okay, this function. So I'm going to create the class for the mathematics. Some of my viewers say they don't like it when I put their utils.js. So I'm now calling it math.js. And I agree. The reason I call it utils sometimes is because it's not just math that is doing there. It could be some other utility functions. I can't really think of any now, but there are situations when I do some kind of simple algorithms there, and like maybe finding the minimum in something, and not a good reason, but yeah, let's call it math this time. And let's implement the linear interpolation. So function, linear interpolation between a and b using t. So these a and b are numbers here. If you don't know about linear interpolation, I made a video about it. It's really well described there, and I give a bunch of different applications, so check it out. But the formula is ridiculously simple. It's like we return the a plus the difference between b and a times t. And the one that works with the vector, so function vlerp, is going to work with two locations or things that have attributes like x, y, maybe z if we do this in 3D or even more. In that linear interpolation video, I also interpolated colors. So there I used RGB. But here what we do is essentially return a new object. So let's make this general. The resulting object that we will return, this one, I'm going to add attributes, properties from A and B, in this case X and Y, but I will loop through them. So I will say for let attribute in A, I assume A and B have the same attributes. Otherwise, I'm calling this function wrong. And then I will say the result of the whatever attribute that is in A is going to be equal to linear interpolation, this simpler function from here, of A from that attribute and B of that attribute from B, using this T. So I'm calling this multiple times for each attribute in A or B, assigning it here and returning it. I need to also include this function, this file here. Let's see if refreshing still works. No, we have, math, not main. Yeah, it works, but I don't know what works. So let's say socks of 0 move to, and it's asking here for a new location. So let's give it an X. So it's hanging here somewhere. Let's put it maybe here on the right, maybe 300X and 50Y, so somewhere up here. So 300X and Y, we set this to 50, like this. I was almost right with my mouse here. So a little bit more to the right. So you can see it moved there. It took maybe a little more than a second. So that says that my computer now is struggling a little bit to keep the 60 frames per second frame rate. Because I'm recording this session and recording my screen and whatever, it doesn't like it. Also, the webcam is on, so yeah. But we have something that works similar to the tutorial where I'm animating those columns, but here they hang instead, so the center is here pretty much. And I can actually do a shortcut here and move this if I want, for example, to be over this sock. So this was sock of 0, 1, 2, 3, 4, 5, 6, 7, 8. If I want to move it to socks of 8, like on top of it pretty much, it doesn't work. Oh yeah, to that location, but now probably something horrible happened. To see what happened, I can try debugging like this. So the location of this is not a number, and I can't interpolate between not a number and yeah. So I refresh and try again, moving it to there, and let's move it over to the sock 8 location. Yeah, and you can see it now overlapping there. So this is quite neat. I can just say go to that location and it will work. It was a little bit different in the tutorial because I had X and Y there directly, so now I somehow remembered that and I thought it's gonna work, but I need to specify here the location this time. No problems. Yeah, so this is nice. And let's implement the sorting algorithm next. So I'm sticking to bubble sort. I really want to do that specifically here. The other visualizers I made in those tutorials, the proper tutorials without experimenting and figuring stuff out, doing this problem solving demo. In those, what did I want to say? I used bubble sort, but I could have used anything else pretty much, maybe with minor tweaks to the animation in the second one. But here I want this bird character to somehow swap, cross its legs when swapping elements. I think it will look funny. So bubble sort has this property that it always swaps things that are next to each other. And you can do that. But if the bird would have to step far away and swap those things somehow, then you need a very big bird, one that wouldn't fit in the screen, or something that stretches its legs like some kind of robot bird or whatever. Maybe that's something you can implement as an extension to what we did today. But yeah, so I know that I'm gonna swap things that are nearby, just next to each other, and bubbles because of bubble sort and how it works. So it won't do any big moves in any way. Always moving next to the neighbor and so on. So let me implement bubble sort, and again I'm gonna implement it in a similar way to what is on Wikipedia. So bubble sort of some array is going to repeat until, in this case, I use a do while loop. So while a swap has been detected and applied, so we have changed the array somehow, then we say here, we assume nothing needs to be swapped. So, and by the way, this is one of the rare occasions where I need to use var. Otherwise, if I use let here, this wouldn't be available because it's outside the scope. Of course, I could have made this declaration above the do while, but I want to somehow imitate the pseudocode on Wikipedia. So for those who think var is useless, here's a use for it, I guess. But I recommend you use let pretty much all the time. And let's start at 1, so we skip over the first element and go all the way to the end. Like this. And if the previous element is greater, then we have swapped something. So this will change into a true, like this. And we do the swap. I'm doing it by doing this trick. It's essentially the destructuring assignment from a new array that contains them in the opposite order. So array of I and array of I minus 1. I don't really like this syntax very much, but I've seen it used a lot, and yeah, I would use a separate function for swapping things. But let's see. I'm happy with this. So now we are doing the swap, and if we go through the whole array and we never find this, then it means that always the previous element is less or equal to the next. And that means that this stays to false, and this while will terminate. So in the end, the array is sorted. Now I want to record the moves here. So I want to know exactly what was swapped and from which index to which index. So this I-1 and this I want to record that move. And I want to record it also when it's not swapped. I mean, every time I compare things, I want to store that move somewhere. So the way we will implement this animation is we first sort the array using this algorithm. And every time a change happens, we log them. We log them, all the changes, and then the animation will begin after the array has been already swapped. It's sorted, but just doing the same things we stored in the log. In this way, we don't have to break this algorithm apart so that every frame we show different parts of the algorithm. So let's keep this log somehow, like log is equal to an array, like this. And here we want to compare these items. So let's add to the log push an object that keeps the indices. So the indices are going to be I-1 and I. And the second thing is going to be, what do? We compare. So I'm going to say here the type of the move type. Yeah, let's just call this moves. So I don't want to repeat move type later. I think that moves is a good name. So, and yeah, it's fine. And the type of the move is going to be a comparison. So comparison. We need to store these as well, because if we only record swaps, then the bird is at the last place a swap happened. But the bird also needs to move to every new location where it will do a comparison. So I want to do this, to keep this record. And then, of course, when I swap here, I'm going to push a swap between these two indices. That will need to be done. And at the end, we return these moves. So now here in the beginning, this array is random, the socks are generated, and now I can call, bubble sort. So moves is equal to bubble sort of the array. And this moves is accessible here. We see 423 moves needed to sort this array. So the array is now sorted because we pass it to bubble sort, but the socks are not sorted. So that's why you see them in the same order, the random order here. And now the animation will begin to use this information here, like a comparison is made between the first two items, and then the second one, a swap is made between the first two items because this is bigger than this one. So you can see here the moves in order are going to tell us what the bird has to do. It's going to compare these two, swap these two, then compare these two, so it will move, and then swap those two. So comparison swap, and that's not always the case. Like sometimes here, for example, probably here, it corresponds to this place, it will compare this item, which will be here, with this one, and this is the bigger one. So no need to swap them. It's just going to leave them in place. So of course, this ordering here, sometimes you might have many comparisons that are happening without a swap. And yeah, so with this move information, I'm going to start the animation, and it will be something like let's take the swap that is happening from the first move. So this one between indices 0 and 1. So these need to change. And that will look something like this in code. We say that the socks of 0 or moves of 0 dot indices of 0, like that, move to the sock at the first move. It's a little bit confusing here. Its location, so move to that location. Yeah. And at the same time, do the opposite. So both socks are going to move. The one from index 0 is going to go to index 1, and the one from index 1 is going to go to index 0. So both of them are moving at the same time. The code will look something like this, but I will make it a little bit simpler, probably taking these indices out somehow. So when I press enter now, these two should swap. Let's see. Yeah, and they do in about a second, give or take. So this is what will need to happen for all the moves. And here in the animate, after we are let's do it after we do this drawing, I'm going to take the next move. So if the moves, if there are moves like this, get the next move. So next move, just the first one in the list. So I'm going to say moves shift, and this is going to take out the first element and put it inside of this next move. And now I'm interested in the type. So if I have to swap, if next move type is a swap, then I get those indices. So let's say the indices are I and j. I destructure and assign to them like next move dot indices, like this. So now I and j are gonna be this the value of move of the next move's indices. So let's just take a random one from here, like 98. These indices are 15, 16. So I and j now would become 15 and 16. And this move is a comparison, so it wouldn't have happened to this one. It would happen only here where we are doing where we have a swap type. So only for the swaps for now, because that's when the socks will move. Otherwise, the character will move. So when we get to the character animation, we'll need to consider that. Okay, so with these indices, what we do is we tell the socks to move. So same what we had here. But now we have a little bit easier code to write. So socks of I, yeah, move to socks of j dot location. And the same happens in reverse, socks of j, socks of I. Because of these tricks that I did here by having I and j refer to next move indices and next move instead of moves of 0. So here I was animating the first move. Yeah, this became much easier to write. But I also have to swap these socks in the socks array, because if I don't do that, then their location has changed, but their order in the array stays the same. So in the future, it's going to think a sock is elsewhere because its index in the array is not corresponding to the X location. So let's also do this the same way. So we did with the array before. Socks of I and socks of j, we are swapping, is equal to socks of j, socks of I, like so. Okay, and now this won't work. I mean, something weird will happen. Like that. A lot of funny movement is going on. It is sorting some things, actually. You can see here how big things are at the right and small things are at the left. The problem is we need to wait for the previous move to finish. And we are not here. We are just doing them as quickly as possible. Every new frame, a new move starts. And for the first sock to get to its destination when we start the first move, it will take 60 frames because of how many we have there. So that means that on frame 1, another move starts. And on frame 2, another move starts. And frame 3, another one starts. But maybe some of those socks are still on their way there. So we tell in between these on these frames, we might tell some sock to go to some location that is not even a proper end location according to the spacing, because we tell it go to where that sock is right now, and that sock is just on its way there, somewhere interpolating in between. So crazy things happen. And yeah, we need to wait for the move to finish. And the way I did this in the tutorial was here we make the draw method tell us if something changed from the previous frame. And basically, if this queue is empty, then it's just going to draw the same thing it had previously. So we say here, let changed is equal to false. And if there is something happening here, changed is equal to true, like this. And we return this. And this tells us if one sock changed. But here, when we draw all the socks, we need to figure out if at least one sock changed. So maybe it's going to be sock number 10 or 15, or 15 and 16 are changing places, or something like that. So we need to know if at least one sock has changed. So I'm going to do the same thing here and say changed false. And here I will say changed is equal to whatever draw returns. So if it's false, then fine. But or the value of changed. So if it's false, this whatever the draw returns and the sock hasn't changed, then false or false stays false. But the first time we get a sock that does change, and this tells us true, then true or false, it's going to be true. So this changed becomes a true. And then it stays true, because even if remaining socks become false, false or true will keep being a true. So this is just a one-line way to write this, and I avoid if statements. And I'm gonna proceed to the next move. So this is here proceeding to the next move if nothing changed. So if not changed and we still have moves, then it's going to go to the next move. And now when we refresh this, it works quite well. I need to use the restroom, so I'll let this play for a bit and I'll be back. Yeah, I think before starting the character animation, I want to implement some physics for these socks. So I will break these socks down into polygons. Or yeah, let's just try to implement physics on this kind of shape in the beginning. These rectangle shapes like that. But this is a little bit of a problem because the sock should actually have somehow these a different kind of definition. Now it's defined by its location and its height pretty much. The width is also there. But I want to implement it so that this is going to be a particle right here, and this is a particle, a particle, a particle, and then maybe it's hanging from the middle somehow, like one particle also here in the middle, at least for now. So it's going to have something there in the middle. Maybe we change these instead of rectangles into triangles. So we have just one particle in the middle where it's hanging and then a triangle like that. And I'm going to apply this Verlet integration on top of these particles. They will be defined so that when we create the sock, these distances, like the distance from this center particle to this one and to that one, all those distances are going to be kept, are going to be preserved. And then we, every time the main particle, this one that is hanging there, is moving, so that one will be fixed. Every time those are moving, the others somehow need to keep the same distances from the main one, the one that is hanging. So we need these particles to also be fixed somehow on the bar, not affected by gravity. Okay, let's see how it goes. So I'm going to go here and implement a particle class, particle.js. Let's also include it here, like so. And our class particle is going to have a constructor that says the location where it's going to be defined, the x and y location, and another attribute that says if it is fixed or not. So I want some particles to never move. That's what I'm saying. So let's call it fixed, like that. And by default, this is false. I will put this default here so that if I define a particle that isn't fixed, I just write the location where I want it to be. And maybe I want to be able to display these particles as well. If we do some kind of Yeah, I might do here a draw function, a draw method on the context as well, so that we can debug a little bit. Let's see. But here, let's just say that this location, so the location of the particle, is going to be equal to the location that we give as a parameter. Let's store if it so that it knows if it's fixed or not. So this fixed is equal to fixed, like so. And in Verlet integration, it's important to keep the previous location as well, because the velocity, like if a particle is moving, we compute the velocity vector from the two locations, the current one and the old one. So when we define the particle, we assume the old location is the same as the current one, and old location is equal to this location, like this. Now we draw it here. I'm gonna make a simple function where I just say begin path, and with the fixed radius, maybe I want to have this as a parameter, let's say 5 pixels by default, and fill style set to, let's say, green, and CTX arc. I'm going to draw an arc from this location, X and Y. So this location dot X, this location dot Y. So this is the center of the arc, a circle, and then the radius. And I need to specify here 0 and math.pi times 2 for a complete circle, and CTX fill in this case. So I will draw these particles just to debug if we are having them correctly displayed there, but in the end we will skin these to look like socks somehow. So we will not need to display these at the end. Now, every time a particle is updating, like inside of this draw, it needs to somehow handle the physics. So what I was mentioning previously, how do we move this particle? Like if it was somewhere else, if the old location was somewhere else, we need to figure out where it's heading now. So I'm gonna make a function here called update. Let's have this as private function, something that only this particle can call. Yeah. Okay. And what we do here is, if it's fixed, so if this fixed, then we don't do anything. We just return, because I don't want to move this particle. It's been fixed. It's not going to move ever, or unless we somehow force it when the bird is pulling on it. And now let's get the velocity vector. So I want to get the vector from the old location to the current location. So I'm going to need to implement some kind of functions that help me do this, because to do that you subtract two vectors. So let's say here the velocity is going to be subtract this location and this old location, like this. I have to implement this probably in this math.js, but then after that we want to also add gravity here. But actually, I think that I will skip it for now and add the gravity later after the first demo. So now let's figure out the new location that we want the particle to go to. So const new location, the future location where we move in this update, is going to add vectors. It's going to add this location with the velocity that we just calculated, like this. And I also need to change the old location so that it's equal to this location, because I want to update the old location. So this old location is equal to this location, and now I can safely change this location is equal to the new one that we calculated. I think this works. Let's see. Yeah. And this update will happen here. This dot update. Every time we draw, we also update this particle. Right. Okay. I really don't know if this will work, but we are not done. We're far from done. I have to now use this inside of the sock. So when we are creating the sock and we give it the X and Y, we will also have to store the sock's particles. So let's generate these, like particles is equal to an empty array and define them. So this particles push a new particle. Let me put this down here. At this XY location. So this is going to be the hanging particle, this location, and I will set it to be a fixed particle. So I set it to true. And two more particles. So these particles push new particle at the bottom left corner. So let me copy these helper variables here. Something like that. And this one is going to be at X is going to be left and Y is going to be bottom, like this. And another one is going to be right and bottom. So there are three particles in this. And when we draw this here, I'm also going to draw the particles. So like that. Now, probably weird things will happen when I refresh, if it even works. It won't work. I don't have to refresh. I know that I have to implement this add and subtract functions for working with the vectors. So yeah. I think I will need more when I make the particles be at fixed distances from each other. But now let's do the add and subtract. They are really easy functions to do. So I just function add. Let's say A and B is the vectors. And what I will do is I will calculate a new vector, so similar to what I have here, the result. And I say these have x and y, and I don't think I'm gonna need it general like this. I could make it general like that as well. There's no problem with that. So let's get all the attributes. And then here, instead of linear interpolation, we just add them. So we add each attribute to each attribute one by one, very simple. And subtract is the same. Maybe you should call them v add, v subtract, but it's kind of okay to keep them like this, I think, because if you add and subtract other stuff, you just put plus and minus. So I think it's clear we're working with vectors this time. I kind of miss other programming languages where you could do operator overloading and use plus and minus on vectors. So here, minus like so. And now let's try to refresh. Yeah, well, something is happening. The particles that are defined in the beginning, they stay the same all the time at the same locations. So we are not changing them in any way, but these are the particles. So this sock here has a hanging point and then 2 points defining the bottom there. And they are not affected by any forces yet, and they are also not moved yet. I will next make them move according to the xy of the sock that is moving now. So this hanging particle, the particles of 0, is the one that has to move. So here, no, in the sock, I will probably refactor this code to something much better later, but now move to, this adds to the queue the values, so nothing changes here, but this is where things change. So this location changes to that, and I want the particles of 0 dot location is equal to this location. So I want this hanging particle to go with the rectangle. And now you can see it's happening. So that particle is being carried along like that, but it should have been connected to these things, and these things should have followed as well. So I need to implement some constraints. The distance in the beginning, like when this sock is created, these distances here need to be maintained throughout this animation, throughout this simulation, throughout this whole process. And I'm going to implement this by defining some segments, some fixed segments between them. Different people call these different things. Some people call them sticks. I will stick to segments as the naming of what they are. And implement them next. But maybe I'm going to first add a little bit more useful functions here. So there are more things that we are going to do with these vectors, and I'm going to implement those as well. For example, we are going to need to scale a vector. So scale a vector A with the scalar value. Let's call this small a. So what happens here is that each element, each attribute in A is going to be simply multiplied by this a, the value that we are scaling. Let's call it s. It's confusing, a and a. Yeah, s for the scalar. It's not a very big word and it makes things cleaner like this. Okay. Then maybe we want also the average of two vectors, like if we want to find the midpoint of something, that can be useful. I think we might need it. Yeah, let's have it here. It's so easy to implement. So the average of two things is going to be just adding up these two things and dividing by 2. We need normalizing also, and we need the magnitude for that. So the magnitude of the vector just means how long the vector is. And it's easy to get using the Pythagorean theorem. I have a video about that if you're curious, just search it on my channel. So the magnitude of a vector, let's call this magnitude of a single vector, so we don't need two things there. It's a distance, it's a length. So let's call this, let length is equal to 0. And every time we go through the attributes of A, I'm going to add to this length the value of the attribute to the second power. I found out recently that JavaScript has this operator for doing the exponential operation. Yeah, and this is actually the squared length, so we need to do here math.square root of the length. So just the Pythagorean theorem, but all the vectors are centered at the origin, so at 0, 0. That means we don't have to make any difference there that we usually do when we work with points directly. Yeah, we might need the function for distance between 2 points as well, so that will look pretty much the same as the Pythagorean theorem. So distance between A and B. Let's see, how do we get that? With vectors, it's easy because now we can actually do subtraction. So what I mentioned previously, we subtract the vectors. Let's say the subtracted A from B, so we just do subtract A and B. So this is a vector that is the one pointing from A to B, and we just get the magnitude using this other function from here. So we already start reusing functions, and that's great. So magnitude of this sub, this gives us the distance between 2 points, written in a interesting way using linear algebra concepts. And I was speaking before about normalizing. So normalizing means that you scale with the inverse of the magnitude. So if you have a vector, let's say it's 30 pixels long, so that's the magnitude, 30. If you scale it by 1 divided by 30, the new vector is going to be just 1 in length, 1 pixel in length, no matter what orientation it has. And it's going to be very useful. It's like the unit value of this, of vectors. So you can make it any size you want afterwards. Just take it, any vector you get, if it's of length 1, of magnitude 1, you just scale it by 5, for example, and you get a new vector of magnitude of 5. So you could control the speed of something like that. So normalize the vector, and this is going to be, I think I just write it in the return. So I scale A with 1 divided by the magnitude of A like this. Okay, I have a lot of useful things here. So normalize magnitude, distance between 2 points or vectors, scaling, average, subtract, add. This math has become a very big file already, but hopefully it's useful. So we needed to implement the segment class. I'm going to go here and say segment.js, and here we are going to force these particles, like 2 given particles, we are going to force them to be at a specific length. So when we created these particles in the beginning, we will record that length and create a segment object that stores that length. And then on every frame, these segments will need to keep it from changing. Like now, when all these top particles were moving and leaving these other ones behind, they need to follow along. So class segment, and this is going to be created between 2 particles. So constructor particle A and particle B. I think this is somehow clear. Okay. Let's put here a little bit of a comment. PA and PB are particles. Okay, so let's store here. This PA is equal to PA. This PB is equal to PB. And the length, like the distance between PA and PB, this is something that I want to store here. So how long is this segment? So this dot len is equal to, we already have the distance function now. So distance between PA location and PB location. That's it. Now we know how long this segment has to be. Let's also have a function for drawing here, a method similar as in the particles, just to debug. So I'm going to move to this PA location .x and y, and now I'm going to copy this with the line 2 and then PB. So going from the location of point A to the location of point B, let's put the stroke style maybe yellow, like really make it visible. Okay. Right. Let's leave it like this for a second and go back to the sock here. And in addition to the particles, add also these segments and visualize them. We didn't add the constraints yet, but let's see them existing first. Segments. And here I'm going to say this segments push new segment of these particles of 0 and these particles of 1. Okay, so this is one segment from the first one that is hanging to the left one. Now also another segment from 0 to 2, which is from the hanging one to the right one, and another one connecting the left one to the right one. So I'm just going to do this. And in the draw here, I'm also going to repeat this for the segments like this. And refresh. And segment is not defined. I forgot to add it here. Like so. Yes. No. Yes, it's happening, but it's confusing because this bar now and these rectangles are also yellow. Let me go back to script.js where we are doing this and say here. I think it's enough if I say ctx stroke style. It's black. No, not enough. So this needs to happen every time we draw a new sock. Yeah. So here when we are drawing this rectangle. Yeah, now it's good. So you can see here the segments to the original location of the bottom left and bottom right particles are always being drawn, but because we haven't implemented the constraints yet, they are very long and somehow like cheese on a pizza since it's yellow. So that's what we do next. We implement these constraints there. I'm going here to the segment. Yeah. And I need to also provide a function here for updating the segment. So same as before, update. If the length is somehow different than what it should be, it needs to change these locations. So let's see. I want to know the current length. So particles have moved. You can see here in the animation how long these segments are. Yeah, very, very long, much longer than what they should be. So I'm going to check this current length. So, and this one here is the one that they are supposed to be. So let's say constant current length is equal to the magnitude of, we subtract the two vectors. So the magnitude of, let's subtract the two vectors. So this would be the directional vector from A to B. Let's say subtract this PA location and then this PB location like this, location like this. And here we put this directional vector to get the current length of how far the particles are currently. And now I could get the difference between this length and the one it's supposed to have. So how much do we have to adjust? Let's say the difference is going to be this current length minus this length, the one it's supposed to be, because it's a rigid segment. And now to move the things according to this difference from here, Like I want to move the particles, either put them closer together or further apart if the segment was for some reason compressed or stretched. So it really helps to have that kind of normalized value of this directional vector. So let's say norm, and I'm going to normalize the directional vector. So now I know the direction that these two particles are pointing, and I have a normalized vector, so one that has a magnitude of 1, which I can scale if needed. And I will scale it according to this difference from there. So the difference from the current length and this location that it's supposed to be, one particle has to move half the difference and the other particle has to move half the difference. I actually have to consider also those particles that are fixed. Those don't need to change, but let's keep things simple and just do it like this. So, yeah, so let's move particle A and particle B according to this normalized directional vector according to the difference. That's it. Okay, so this PA location is equal add. We have additional adding vectors function there, and we are going to add here to this PA location we scale by half the difference. So I think A goes opposite direction. If I'm wrong, if I'm right, if I'm wrong, then I have to switch these. So scale this normalized vector. So this one has a unit 1 with, I think it's minus the difference divided by 2. So if I'm wrong, I have to switch these around, but it's usually obvious when testing that something is wrong. And this one is with plus. So one of them moves towards the center, the other one towards the center in opposite ways. So that's why plus and minus are needed there. But it could be that they should go opposite. So it depends if it needs to contract or expand. And let's update these every time we draw them for now. So this dot update and see what happens. So refresh. Doesn't seem to work. Oh, I'm saying what I'm doing, and I have here, like, I mean location, I talk location, and then I accidentally type it when I know that the attribute is loc. So this is what I mean. Now you see these, this triangle here going towards the right, and these are now pulled that way. So somehow this still stays a triangle that is similar as in the beginning. And it's also, yeah, we did it. I'm gonna do something. Go here in the socks and not draw them as rectangles anymore. And here, when we are drawing the segments, I'm gonna make these orange, a little bit darker color. So the rectangles are now confusing because we already have some kind of shapes here, and they are overlapping with those rectangles that no longer are so true, because these are somehow obeying some law of physics, some laws of physics. Okay, good. Gravity. So we also need to make these go with gravity. It seems like I don't need to worry about moving them. So what I said just now, this PA location, I'm changing PA and PB even if PA is fixed. A little bit I'm adjusting it. This could be a problem when our socks become more complex. Let's see. But basically, I don't want them to change. Let's fix this now. So this happens if both particles are not fixed. Like, for example, these two at the bottom, they are not fixed. If that segment between them expands or contracts, it needs, both of them should move. But if this PA is fixed, okay. Okay, let's say if PA is not fixed and this PB is not fixed. So we have this case already. It's what we wrote at the moment. Else, if this PA is fixed, then PA is going to stay at the same place, but PB is going to move twice as much. So I need to still keep that segment the same length. Only PB can move because PA is fixed. And same goes other way around. So if else, if PB is fixed, then PA minus the difference, like this. So I hope this is clear. And this is actually better. You couldn't see very well before, but sometimes these particles at the top were fidgeting just a little bit, because after each move, it would adjust, and then it would move a little bit lower. It was very, very subtle, but I could see it, and it could have caused problems in the future. So I wanted to fix this already now. Okay, I was talking about gravity, so I think I should create a physics class. Let's see. I'm gonna go here and say physics. It could help to clean up some things. And physics.js. And class physics. Maybe I don't need a constructor here. Maybe it's a static class. So static gravity is equal to, let's say it's pulling down on them with, I don't know, 0.2, something like this, every frame. So yeah. And now in the particle class, when we are updating the particles, we add to the previous location the velocity, but we also add this gravity. So let's call this gravity. It will change the new location with the gravity vector, but G is there implemented like mentioned just as a single number. So here we would have to say don't change on X, so like that, but on Y change with that gravity. Okay, hope this works. Doesn't work. Gravity is in the physics class, so no. Doesn't seem like it's affecting at all. I was expecting things to add to affect here. So I'm adding to this new location. A gravity vector with nothing on X and then something on Y. I'm gonna change the value here to something big, but it's not that. Why doesn't it work? So let's debug. So I'm gonna go to the particle class here in the update function. What? Hmm. Debugging here, so the particles here, all of them are fixed. Why? Ah, I probably copied there the true. Yes, so it's working as it should, because they should be fixed. And the reason why here it's still moving them is kind of interesting. Yeah, it's actually moving them because let me go back here and test something real quick. So this should be the same as before. But here, if I'm gonna write like if not PA fixed and not PB fixed, now it doesn't move them. Okay, code is actually the same, but it's not the same, but similar as before. It should still continue to work. The thing is, there I was checking if PA is fixed, and if it is, then PB should move, but PB might have been fixed. So yeah, a little bit of confusing stuff. These don't need to be fixed. And now the code goes here. So I remove the breakpoint and test. Okay, and now these things are somehow wobbling, kind of like pendulums, but this is way too much. I don't want to make some interface that is not understandable. I want you to still understand the algorithm from watching this visualization that we create. I don't want just to have something fun, but also informative. And when everything moves like this, it's crazy. So not like this. I don't like it. I'm going to need to either increase the gravity. Let's try that. So I'm gonna go here and say the gravity is 10, for example. Okay, this is way too much. It's actually pulling these. You can see the 10 pixels that they are being pulled on each frame, actually. Okay, 1. It's a little bit better. I think I'm going to stick with this and make these look more like actual socks next. So I don't want to fidget with these settings too much because these socks will be made of multiple segments. So when that happens, I will need to readjust these. The physics will not look so great. But yeah, let me decrease this a little bit, 0.5. So I still see some horizontal moving. Like a little bit of wobbling here is happening now. I want it to stop sooner, so we might have to implement some kind of dampening. But I want that to be our concern only if when we implement these segments, like allow the socks to curve somehow. That's my vision here. So let's extract this code that generates these particles and segments to a private function. This create particles and just copy it here. create particles. And now I want to generate these particles in a loop. So somehow I want to add rectangles on top of each other. Keep a triangle, a small triangle to begin with, but then rectangles at the bottom, like some kind of building blocks with the triangle at the top. But we start at the top because we know where that is. So how many of these blocks we need depends on the height of the sock. Yeah. So instead of going to the bottom here, left and right are useful. And then these segments, we need some other way of figuring it out as well. But these particles here, I want to make this into a loop. So I know the height that it's going to have, this height. So let current height, like where we are drawing the particles, is equal to 0, while current height is less than this height. Current height plus equals this segment block height. So a little bit confusing here, but this block height, let's put it to 10, for example. And right here, socks are made of blocks. Let's comment a bit more and draw a block here. So maybe something like this. It's good to have informative comments like this. So this is a sock with 1, 2, 3, 4 blocks. Block 1, block 2, block 3, block 4. So while we are less, current height is like that. And this is where we are going to draw. Our particles, and the y is going to be this current height. Yes, okay. This should work, assuming this height is not 0, which could theoretically happen. So let's replace this with the do. So we always do this part. And then while the current height is less than the height. Okay, so now we get particles here added somehow. Okay. X and Y is, X is coming from this location dot X now. Okay. Wow. Yeah, this shouldn't start at 0. Wow. So this should start at y, because that's where we're putting the first particle, and then the next ones yeah, plus this y location y. So we start off here, this location y. Yes, it's good. The problem is we need to define segments also for those things there. So the first segment, from the first particle to the second, and from the first particle to the third, the triangle at the top, I think that these are fine to be as such, but then from particles of 0, 1, 2, from 3, 4, 5, 6, 7, 8, this needs to be done in a loop. Actually, I think yeah, all of these are good. The triangle is good. So now we just have to loop this bottom part that will look like a kind of a U shape. So this thing right here, these connections we need to add with the loop. So for let I is equal to 3, I is less than this particle's length, and I want to jump every 2 particles, because at each step of this loop I will connect both of the 2 particles using segments. So let me just copy one of these for reference and say I want to add this particles of I want to connect it to this particles of I minus 2, which is the one directly above it. Yeah, and I also want to connect these particles I plus 1, so the one on the right, to the one above it, so I minus 1. And I need also this connection from I to I plus 1, so the bottom bar. I to I plus 1. Oh, look at that. Crazy. Okay. It's very springy. This springiness, you can control it by calling this update function multiple times in the segment. No. Okay. Why not? Drawing the particles, updating the particles. Then drawing the segments. Aha. Okay. I need to separate this update function actually, and not call it here. I'm gonna delegate this updating of the particles and of the segments to the, yeah, I don't need to draw these anyway. This is just for debugging now. So I'm moving these to the physics class. So let's have here an update function. So static update, and have here particles and segments. And I will say for let I in particles of I dot update, like this. And I think I can actually pass here G. It makes the code a little bit cleaner. So here, let's call this force, so that this doesn't have to worry about what physics is. So that force comes now from the physics class. And the same thing will happen for the segments. I don't need to give G there because segments don't care about it. But this update has to happen somewhere. So I'm going to go here where we're making the animation. And every time I'm drawing these, um, physics update. Yeah, let's see. I might have to split this into an update and a draw as well. Particles, and the same for the segments. So let me just Okay, now these seem to be connected. I'm not sure if you noticed before, but the segments and the particles were disconnected somehow. And I wanted before to repeat this update for the segments multiple times. Ah, yes. And of course, repeat it for each segment again and again and again. Before, I was just updating one segment multiple times without considering the others changing. So we can control here rigidity, like doing this multiple times. So I will explain what happens after it works. I hope it works as expected. It should. I've been playing around with this for a long time. Yeah, so now it's much more rigid, you can see. And if you put 5 here, then it's a little bit less rigid, a little bit more bounciness happening there in the beginning. Maybe something like this is fine. So yeah, this is not bad. Let's try a lower gravity actually, maybe 0.3. No, these should really stop faster than that. It's disturbing me that they are so moving such a long time afterwards. So maybe I want to go in the particle class and say let's try to no, wait. Okay. This is also going to be impacted by the animation speed. So maybe I'm going to play a little bit with this one first. So when I'm moving the socks, I have here a frame count. Maybe I want to use 40 frames instead. So now this movement is much more emphasized because I'm pulling on those particles much faster. And now on top of this, maybe I'm going to put a stronger gravity, maybe like 0.7. Yeah, maybe even more, 0.9. Yeah, I think this is just fine. Okay, this is just great. Hmm. Let's see bigger happens. They stop much quicker there. Okay, I think I'll just leave it to 1 for now. And I think that when the character moves, there will be some intermediate steps. The character moving to a new location, and then it's gonna make things look a little better. So once this thing starts to move now, it's just moving kind of constantly until the end pretty much, or until it finds one where a swap happens. So then there's not enough swingy effect. But when the birds will cross two socks, then it will have to uncross its legs or move somehow differently. So basically, that stopping is going to allow the socks to balance more. And I think I don't have to worry about this too much. And what is happening at the moment, it's just fine. Okay. Good. Good, good. Now, how about the bottom part of the sock? Let's give it also a little bit of a shape. So inside of the sock here, yeah, generating these particles. How about if I set the last two particles, so this particles of this particles length -1. Let's just try the last one. Let's just say here const last particle is equal to that one, so I don't have to write all the time, and say last p dot location dot x minus equals the block height. Okay. And the same for the second last particle. So -2 here. Yeah, I wanted to move these last ones a little bit to the left, and it happens just fine, but they need to keep the same angle. I wanted the bottom part to be a little bit at an angle, so it's the tip of the socks. And the problem is that these segments don't enforce that kind of constraint there. So they go back down and they pivot back down like a pendulum. So what I will do is add one more segment at the end, connecting the last two particles, last P and second last P. So no. They are connected already. So I just need last P and these particles of this particle's length minus three. No. So this is length -1, -2. This should be -3, so why doesn't it work? Also, these socks here, I have to figure out how to deal with that. But here I would have liked to put a diagonal between the last two. Did I count wrong? Let me try -4 here. Okay, yeah, this is the last P here, and then this is -4 right there. All right, so I'm getting some errors sometimes because if I just have that small triangle, there is no -4. So only then I do that. And when I define the array in the beginning, I have to somehow make sure that I don't generate these small things here. They don't look like socks. So when I generate the values in script.js in the beginning, I'm going to say here the random values. Let's use lerp and say between 0.2 and 1 using a random percentage. So this is now gonna have, maybe this is enough. No, some of these socks are just too short. I think the 0.2 is fine. Okay. So this is good. But I would really like these socks to come in pairs. So let's just say here I divided by n -1. So this is going to be our t for the linear interpolation. And so what happens now, the array is actually sorted. Yeah, I'm happy with this somewhat, but so what happens is if I go here in the sock and actually re-add drawing that rectangle, which I removed. What? Why is it not? Oh, yeah, this destructuring here. Yeah, I think it's fine, but it happens over the particles and the segments now. So I'm behind them. No. Yeah, and it's not black, so I can't see it well. So if you look at these rectangles, they are actually not the same size here. They are in increasing order, but if you look at these socks and the way they are structured, they look like these are in the same size category, even though they're a little bit different. This is fine, I think. I mean, we could work with this, but I don't really like it so much. So I'm going to be specific here and go to n divided by 2, like this. And then put here that twice. So now I really get exactly the same. You can look at these rectangles. They are 2 of the same size. I should also probably put here n divided by 2 minus 1. Okay, to get the same thing as before. And now these rectangles, so these values in this array are actually identical. And in pairs, like socks usually come in. So this is fine. I'm happy with this. But the array is not random anymore. So let's randomize it. How do I randomize? I don't know how great this randomization algorithm is, but I just do something. So getting a random index here, and I just say array of I and array of j is equal to the same thing with j and I. So I swap these items. Basically for each I get the random other index and I swap them. And I have an error. Okay, I'm not sure why there was an error. I think it has to do with this semicolon interacting with this next line. So use semicolons in JavaScript whenever you can. I mean, make it a good practice. So now we get this, and yeah, you can see now this big sock going at the end, and then the next big sock here is gonna end up next to it. It's good. I'm happy with this. Quite happy with this, actually. Yeah, I'm really happy with this. Debugging this kind of drawing of the sock is somehow... Let me keep this code here just for reference. I might need it in the future. But what I want to do now is draw just the outline of the sock. So So here the particles go left and right and left and right and left and right. I want to start off with the right side. I think it makes the code a little bit easier a little bit shorter. CDX begin path, and I'm gonna move to this particles okay, let me get a reference to these, like particles. This particles, like so, and move to this particles of 0, and then for let I is equal to 2, I less than ps dot length, I plus equals to 2. So I'm jumping, so I'm always on the right side. I want to do a line to that particles, like so. Line 2. And then CTX stroke. So I'm just drawing the right side of the sock. Doesn't work. Yeah. So. All right. So it's something. And now for the left side, I'm going to go opposite direction. So minus 2 greater or equal to 0 minus equals 2. And probably I can do here close path to go back to the first one. Yeah, like so. They look a little bit like socks. But this bottom part, I would like to emphasize it a little more. Let's see here where I'm moving them by this block height. Could I do it ×2? Nope, not enough. The other one as well. Yeah, not the best looking sock. Let's try the second last piece, Y value. So this one right here, I want to move it more upwards. Too much. Not the best. Let's put the debugging on a little bit. Let's try the same with this last P also on the Y. And debugging off. Yeah, I think I leave it like this, but I will somehow most likely change the way I do the drawing at the end. I'm not very happy with it. Yeah, and let's define also some colors for these socks. Yeah, so we will fill here and make this CTX fill style this color. So this color is going to be something that this sock is going to get as a parameter. Okay, and here in the script I'm going to say colors red, green. Actually, I have this on my website. I have this machine learning demonstration somewhere there. This one has many colors here. So I'm gonna open the app and take the array of colors from there. It's probably somewhere, hopefully easy to find. No. Yes. So let's try that one. This seems not good. They're keeping the naming convention. Okay, so now here I give to the bars also the colors somehow. Huh. Hmm. Not great. I would like to duplicate these colors somehow. And I have to swap them also. Yeah, difficult. So I need to remember each of these. Okay, so let's, not very nice, but sock colors. Empty array here, and I'm going to push here the colors of I twice. And then when I swap here, I also swap the sock colors. I should use objects where the array has the value and also the color, and then they're paired together. The problem is that then I have to change some things here or use some more advanced methods, and I don't want to use them now. And now this sock color is also swapped. Great. And here where we are generating the socks, we are going to give it the sock colors of I as well. Yes, yes, it works. And I even remember these, that the red is the first one, blue is the second, orange is the third one. So it's working just fine. Good. Great, I'm happy with this. Let's move on to animating the character, to creating the character. And I will start it now and do as much as I can before I'm going for lunch, so about an hour or so. Let's try to get somehow the basic skeleton of the character, and then I have some time after lunch and I hope to wrap it up. It might not be a very polished thing by the end, but let's see, maybe it will. I hope I have enough time. I really want to finish it today. Okay, anyway, this visualizer already is something nice with a little bit of physics there. I think I really want to move this point lower. Let me just do this one thing. Maybe it's a good change and I don't have to worry about it anymore. It somehow bothers me. So that's actually the second last. plus. It's not bad. It's not bad. I like it. It's good. This tip now is way too much, isn't it? 2. Wow. Wow. I like it. Okay. Great. I can move on. This looks like a sock somewhat. A little bit sharp point there, but I'll let you play with those if you want to make something even better. It's a pointy sock. Gonna hurt with when someone kicks you with it. Okay. And let's draw here a little bit. Something like that. It's not exactly the same because I'm moving now this point a little bit also, but yeah, great. Fantastic. Okay, so character animation. Phew, how do we do this? Let's import a new file. Character, let's call it bird. bird.js. And bird.js. And in the script, in the beginning, we're initializing all of these, like the arrays, the colors, the socks. So before we have the moves, I'm gonna also initialize the bird. So const bird is equal to new bird. And actually, after the moves, it's also fine. This sorting will happen instantly, so it's not going to be noticeable that the bird takes some time to appear. And I want the bird to be positioned at the first move. So moves of 0 dot indices. No, I need the first sock, xy. So socks of 0 and socks of 1. So this location is going to be, yeah, interesting. Okay. Socks of 0 dot location and socks of 1 dot location. So I know bubble sort starts in the first two, compares the first two elements. And I'm telling the bird to create itself at these two locations. The location of the first sock and the second sock. Now this will not be the bird's center point. This bird character will have two center points. They are not center points, they are the feet, the location of the bird's feet. It's somehow this object has two centers, if it makes sense. Two reference points. I've never done this before, but I'm curious how it works. So that's because I really want to synchronize the bird's feet and with the sock movement easily. So if I have one like XY location for the bird, then I have to somehow think very complicated stuff relative to it, and I don't want that. So two of those things, and maybe I want the height of the bird also as a parameter. So let's give it canvas height times 3 times 0.3. So a third of the canvas height. We have enough space there. These three things are what will define the bird. And that means I don't need it to be after the moves because I'm using the socks locations. Good. So this bird class, we need to define it, but let me also draw the bird in the animate. So when we are drawing the socks, I'm also going to draw the bird on the context. Nice. So bird object class bird constructor. So left foot location, but I think it's implied, and right foot and height. So let's store here this left foot equals L foot, this R foot, this height. So I'm storing these as class attributes here. And the draw method, the draw on the context. Now I would really like to know where the head of the bird is. Let's give this an update method. I think it can be private because I plan to call it in this draw. Bird will know how to update itself, its position, no context. And here, this head, its location, the location of the head, will be, let's make it always be in the middle of the left foot and the right foot, but at the height. No. I want this to not be the height of the bird. I want to be the vertical location of the head. Head Y. Might be a little confusing. Yeah, so the head here is going to be an object with x is equal to L. We have the average function, average of L foot R foot. So this gives us actually the whole point, but the y of the head comes from there. So when we update, we also do that. So this average does a little bit extra work, but I kind of like it like this. At least I find it easy to read. So it averages this, but then it forces the y to be at a specific place. And let's begin path and ctx arc. Let's draw the head first. Let's give it a radius. 10. And this head x, this head y, radius 0 math pi times 2. So the full circle. And let's fill it like this. Let me refresh and see if it works. Okay, something works. At least there is a head here hovering between these two socks, but it's too low. Yeah, I want it to be maybe here. Yeah, so let's define this bird a little bit higher up, maybe like this. Even higher. No, I don't like it so high. Maybe like this. But now I don't like that spacing here is not so much at the bottom. Also, this head here is a different color now, so it's changing depending on the last sock that is being drawn. Okay, so maybe moving this bar a little bit higher up. String height, was it 40 before? Yeah, this is better, but now the bird can go a little bit. Of course, what I'm doing now is pretty much personal preference stuff. I like this. Okay, so the head is here. Let's draw the legs. We know where the left foot and the right foot should be. CTX, begin path, CTX, move to this head X, this head Y, and line to this L foot X, L foot Y, and CTX stroke. I'm just gonna copy this even though I could do it in the same path, but I'm probably gonna style these better later. Why is it not drawing them? Line 2. Yes, so now the bird is sitting on those. Yeah, okay, interesting. So, we have these move to in the socks. How did we do that? We do something similar for the bird, I think. I'm going like this, move to, but I want left foot, right foot. So I want those to be the things that are gonna move. And we add a cue here too. Like this. So let's just, for now, vlerp this left foot to the new left foot location, like this. Okay, so this will be the left foot, then the right foot. So we get in between values for these, left foot and right foot. And we add these into the queue, but we need to know which is which. So I'm gonna push these as left foot like so, and then comma at the end, and then right foot like so, and then close this like this. So the queue for each frame has a value for left foot and a value for right foot, and they are points or vectors with x, y coming by interpolating between those locations. Yes. Okay. Now, what did we do before when we made our socks? We were drawing them by updating relative to the queue like this. So going back to my bird, I'm actually going to do this in the update function. We're not using it yet, but yeah. So if this queue has a length, then this, okay, frame, this info, frame info, we get it from the queue, and then left foot, so this left foot is equal to info dot left foot. Same goes for the right foot, and this is not something that we need. Might be useful to keep this changed. I don't think we need it, but or yeah, maybe we do, because sometimes we wait for the bird to move later on. Let's see. So update, yeah. And every time the foot is moving, and then the head will always be at the same height, and depending on the new location of the foot, the right foot. So it will look very boring in the beginning, but I think we can tweak these somehow with some smarter mathematics later on. And here, calling this otherwise. Yeah. And we might have to do this. Could be a good idea. I might not use this part, but I think we will need it when the bird is moving, but the socks are not. So that will be also a move that we need to consider. Okay, so did something here. If I refresh this, head Y is not defined. Okay. In the beginning, the queue is empty. So I can just call here this dot update. It will do the average and this, but this needs to be stored somewhere. So okay, that's fine. But now we need to also move the bird. So here, where we are doing these things, let's first do the movement. There are just two types, this comparison. Let's just leave it with an else, and that's it. And right here, bird is moving. So I'm gonna say bird. Okay, let's take this out because it's gonna be needed by both cases. And bird move 2. And now we need to get the socks of I and the socks of J locations. Is this enough? We actually need here to detect the change also from the bird drawing. So good that I wrote that there. So if the socks are not moving, keep the fixed location of them, that one particle that is fixed on the string, because they can still move, like the physics on them that doesn't apply to this. So same thing with the bird. If it's done moving here, big problems, so nothing happens. This location here, I forgot to type it. Hey, something is doing. It's doing it. It looks like something that is already. Oh, what was that? Yeah, so very simple at the moment, but it looks like the thing that is doing the change is moving where the change is happening. So it's already a good teaching tool. I like it. I don't like that the bird is doing this dash to the beginning. So I'm going to modify the bubble sort algorithm a little bit. First thing that I also don't like is this part. You saw at the end, the bird is just going over this part of the array that is already sorted. So this is actually a small optimization that you can do in the bubble sort algorithm. It's even listed on that Wikipedia page. So every time the bird reaches the end, it will never need to reach that point ever again because the biggest sock will get there at the end of the iteration. So in the bubble sort algorithm, here, this array length, we can initialize it with n is equal to the array length. And every time we do one of these sweeps through the array, we can say n minus minus. And that will make our bird not cover this part right here, the one that it's animating now on the right. So it will immediately have went left here. Let me refresh and let it animate in the background while I do the next part. So what I want to do next is once it reaches the end, I actually want it to go in reverse. So it's not going to do that dash anymore, but it's going to start going slowly back and forth and back and forth and back and forth and back and then stop in the middle. Somewhere in the middle. It may stop earlier if the array gets sorted before that. But that way our bird doesn't dash like crazy and I don't need to worry about that kind of animation. And it also doesn't make sense. I mean, it makes sense to continue from where you started, from where you're at, and work on the array there. So we're gonna have to check depending on this n, if n is odd or even, yeah, I think then we're gonna do something. So let's try here. If n is odd, if n is even, because in the beginning it's even, it's 20, then we do what we have at the moment. Else, I'm gonna copy this, but go from n minus 1 greater or equal to 0, I minus minus. Now here I don't need to decrease n, but I would actually need to have another n on the left. I'm just going to name this left is equal to 0. No, it's equal to 1 because we always compare with the previous. So we go here from left, which is 1 in the beginning, and then we go until left, and then increase left here in this case. Is this correct? I don't know, but we'll see it in our example. Yeah, so now you see this bird just doesn't go anymore all the way to the end, so I think my code worked just fine. I just watched the animation now at the end, but it's not all the way to the right, so it's good. So a new algorithm, it's the same bubble sort, but now it's going on both directions. I hope it works. So it's taking now this pink sock to the right, and then it should start to take the red sock to the left. Yeah, so it's now taking the orange sock to the left, but we'll meet this one, and now it takes the red sock, and it's gonna take it next to the other red sock. And what happened there? No, something is bad. Yes, so left changed, but n didn't change. So this needs to consider the value of left also. Minus left. And this has to change now, I think. Let's try again. And let me see if I can make this animation faster. So it's fine. I'm happy with this. I don't need to test quicker than this. I hope. If this doesn't work, then yes. Okay, so now it's taking the blue one, but it will switch with the red now. And now it's gonna take this red, one of the reds, doesn't matter, uh, all the way to the beginning. And now it's gonna take this lime color all the way to the end. Let's just look at it work and see if it's doing as expected. Yeah, and now it takes the orange and it will switch it with the blue. I mean, the blue will, yeah. And now it takes the red, the second red next to the other red in the beginning. And then it's gonna grab this next lime and take it. Eventually, it's gonna drop this gray one and take the lime instead and put it next to the other sock there. And now goes left. Yeah. This looks good. It's smarter than before. It doesn't do those running all the way to the beginning like some robot. Of course, it's not as smart as it could be. Maybe you can take this up a level and think how could the bird do it in the minimum possible, in the minimum number of swaps that can be done. That would be a tricky. I don't know if it's hard to implement, but it's a nice task to think about. I want this to be anyway a sorting visualizer, so I'm not going to do some optimum sort, which is not a real thing. It would be, I think, you would need to sort the array and then compare and figure out exactly where each element needs to be at the end, and just with one loop through the array, put everything in their final position. So I think that's how I would do it, but that's not the real algorithm for sorting because it's linear time. So sorting has to happen before, like off screen, and then the bird just magically knows where everything will be at the end. Okay, this is working great. But I still want to do a couple of things before my lunch break, so let's see if I can do it. The bird crossing its legs is one thing. Let's try. So in the script here, bird is moving, but bird should also move here. Now I could put it after the swap and then I don't have to change this code, or I just replace this J and I think this should work. So, okay. So easy. It's kind of looks like walking now. Okay. More stuff. What we do? Yeah, this looks very good. I like how the sock stays in the same foot, in the same foot there. Much better than before. It's so clear what is happening there. Okay, now I would like the bird to have some knees, like the feet to bend. I think the bird will face us all the time, and the knees will point to the side somehow. Um, so let's see. In this update, okay, this head is defined right here, but I should know that there is a head in the constructor there as well, defined later in update. So yeah, but also this left knee is null and the right knee is null. I want these to update automatically. I don't want to worry somehow about how to generate those on each frame. I'm gonna try to calculate them using geometry somehow. So here, after we know where the head is and after we know where the feet are at each frame, so let's start with the left knee is gonna be the average of to see the knee, I need the leg to be somehow longer than it is now. So after the update, I need to know this new leg size. Distance from this left foot to this head. So this is going to give me the leg length that is now, but let's multiply this by 1.4, for example. So longer than what it is. And then we're going to update again, just a trick that I'm doing. But when we update now, I want to check here if the leg length is defined. So now we are going to I try to explain later, but I hope I can. So if we have a leg length, then this left knee, if we don't have the leg length defined, then this left knee is just the average of this left foot and this head, so in the middle. And the right knee is the same, right foot and head. So this is if we don't have that kind of leg length defined, which comes after the first update method. So we have some values for these. Otherwise, so I have the value, I want the knees to be offset a little bit from a center point. So let me get left center, and this is going to be the average of the left foot and this head. And now from the center point, I need to know the angle of these as well. So the angle of the leg, left angle is the arctangent of y minus head y, and the same for the x. Let me just put these right here. So that's the angle from the left foot to the head. I need to go away from this center point at a 90-degree angle from this angle, a certain distance, so that the hypotenuse in this 90-degree triangle is going to be equal to leg length divided by 2. So I know the hypotenuse and I know the distance from the foot to the head. So I need to know just half of this distance. It's fine like this. So let's define here the offset angle is L angle plus math divided by 2 plus 90 degrees, I think. Or minus, I will just flip the signs if it doesn't work out. I can't do this in my mind very well at the moment. Getting tired. So here, offset angle, I have the distance. And I know the leg length. So I need to know how much in this direction of the offset angle I move. So kind of like the second leg of the right angle. So if it's a ABC triangle with leg length by 2 is the hypotenuse, then L dist by 2 is one leg, then the other one is going to be height, the height that way, that I'm going to go from the straight leg is going to be equal to math square root of the hypotenuse, so this leg length divided by 2 squared minus this L dist divided by 2 squared. So this is now giving me how much I have to go from the center point in this, okay, these are, L dist is not with this. In the direction of this offset angle from this center point. So, so this L knee is going to be L center dot x. So the x is going to be L center dot x plus math cosine of the offset angle times this height that we are going away from the center point. So yeah, and the same for the y, but this is gonna be with the sine. I believe so. I really hope all of this works. If not, I'm in trouble. Have to redo it or play a little bit with this. Okay. Let's just average the right knee here for now. I'm gonna focus only on the left knee, and when it's good, I copy these things for the right knee as well. So yeah, and now in the drawing here, I move to the head and then line to left knee first, and then to the left foot, and then right knee, and then to the right foot. Yeah, so now if I save this and refresh, oh my god, it worked. I think this is the luckiest day of my life. So this percent here that I mean, I'm going, I think 40% over. Let's see. Yeah, this 40% over, it's way too much. I'm gonna put here 20%. And now, yeah, now this knee is, yeah, it's a little bit more inwards, maybe 15% over. That's just good. So this knee always will position itself so that these two sides of this triangle are the same. I calculated the height, like if you complete that triangle from the top of the foot. Like if you think about this triangle right here, this height, how much I have to go, this is calculated using the Pythagorean theorem. So it takes the length of this hypotenuse, which we know because we say that we want it to be 15% more than the straight line from there. So it's easy to calculate. And we know the straight line distance. So I'm halving both of those things so that I focus on just half of this triangle. And I figure out this height. That's all that messy code there is doing. So, yeah, let's actually, and getting the, also the absolute angle, like this vector here from this center line towards this, that's offset angle. So it changes all the time this animation is moving. So we need to get the angle and the height at which to change this center point. So from the center, an angle and a height relative to the foot location and the leg length. So a lot of messy stuff here. Maybe I can make a helper function. So get angle and height from a very bad name, but from the center no, from the head and foot, like this. And here I'm going to call it like result is equal to that from this dot head and this dot left foot. Okay, and all of this stuff here is going to go down. No, let's just call this get knee. I think this will work. So get the knee from the head and the foot. And this will just become left knee. So let me copy this here. Return this object. So given the given foot and the head, which is the same as this head, but it's easier like this. Then here I don't need left anymore. I just have, okay, just a second. So let's refactor this with rename symbol center and this one angle, and then this one is some distance. Yeah, we can call it base actually. It's fine like this. And then height. Let's rename it to base. It's a little bit better. Yeah, this is now fine. I think so. Nope. Yeah, this dot hashtag. Okay, now it works, but we can replace this for the right knee as well. And I think I need to change something, otherwise the knees will bend inward. I mean, we'll both bend to the same. Oh my god. Oh my, what is happening there with the right foot? Yeah. What is happening? Right foot. Yeah. So a little bit funny bird. No, I want definitely the right knee to point outwards towards the right. So I need to change something there. Maybe I pass here angle offset math.py, an angle offset. By default, this is going to be 0, but if we pass another offset to the offset. Yeah, let's rename this to height angle. Height absolute angle. Okay. Yeah, that's looking good. And here I think I'm gonna just put 10%. The knees are going too far outwards. Even 0.9. even maybe 0.7, let's see. 0.6. I kind of like that. Okay. Hmm. Yeah, looking good. So I'm gonna go for lunch now, and then when I come back, I'm going to try to make this look nicer. So somehow style that character and make the character's movements a little bit more polished, maybe some kind of easing or I don't know, bouncing or I don't know. But this is not bad. I'm happy with this already. And of course, this I would like to have it look like a bird. So let's see how it goes. So gonna be back and continue with those things. I think the hardest part is done already. Yeah. It should be like starting at 0 and going back to 0 and in the middle at 1. So I think that this t value needs to be multiplied by math.pi because that's the interval in which sine goes up and down until 0 again. So from 0 to 1 and back to 0. And then this would be math.sine of that. Nice. And I want this to be used somehow in these feet. So let me take this value out like this. I will call it frame like that. And then I will push this frame into the queue. So same thing as before. But before I do that, I change frame left foot dot location. No, it's already a location. That y. I'm gonna subtract, so make it go upwards. This u multiplied by some value, let's say 10 pixels, and see what happens. I think this should actually be a fraction of the leg length because we might change these in the future and it makes things more easy like this. So let's say 0.1. It's probably too much, but yeah. And just to test. And same from the right foot. So the y minus equals this length times u. So u is going to change this length from 0 to its value and then back to 0 its value that is just 10% of it actually. So this. And now let's see what we have. It's kind of funny. I like it. It's interesting. Of course, I'm gonna have to figure out how to glue those socks. But, let's see if I want the bounce. So, do bounce. And if we want the bounce, then I do this thing. So, this bounciness, I'm gonna control here where we move the bird. So maybe when we swap, maybe I don't want the bounce there. So I want it here, like that. So now it's dragging those socks. And I don't need to do anything. And then it's bouncing to the next location somehow. Yeah, that's fine. But the head value, I mean, I don't like the head. Head should also bounce a little bit. And I may play around with this easing a little bit. So here each frame has the information about the head, about the left foot and the right foot, but not about the head, really. Head is always like adjusted separately. And I don't think I want that. I think I will actually take this out. And here where we get the left foot and the right foot, I'm also going to add the head to the frame. So frame of head is equal to, let me undo, take this value actually. So frame of the head, and then it's going to be the average of the left foot and right foot. And the y, I actually want to keep the average of this. I don't know why I didn't do this previously. Minus height, like I had in the beginning. So yeah, I want to keep it like this. This will make the head move it as well. So and actually I want to do this probably after the bounce thing happens, because this left foot right foot is controlled by, is changed by that. But this height, yeah, what was it before the height? It was head y. Is this head y used anywhere else? No. So back in the script where I'm defining the bird here, now I want to give it a height instead. And this is gonna be very small, I think. Oh, we have an error. Yeah, okay. Mhm. Yeah, I didn't finish here, so okay, so this is what the frame has, and then here I have to update the head also. Mhm. Oh, and they are probably null in the beginning, so hmm, okay, yeah, so the head there is missing. Mhm. Yeah, I think that we need to initialize it like this. Hmm. Mhm. We need to give the head a value in the beginning, I think. Ooh. Okay. Yeah, very short bird. So let's make this bigger. Yeah, and I would like to get a different easing function here. Somehow I'm not happy with the sign there. So easing functions, JavaScript. There's this nice cheat sheet here. And I would like to have a kind of a elastic. Let's try something like this and see how it looks like. But I would like it to go back as well. Let's just see if we can use it somehow. So this is some function here. Let me just put it in the math. And this is TypeScript, so I don't need to define these types here in JavaScript. And this POW is in the math library. I think that's fine. So if I take this one and why is this complaining here? Yeah. So now if I take this function and I give it to the bird here instead of what I had previously, according to T. No, not good. They don't have a function like the one I'm looking for. I'm gonna have to figure out my own. I'm gonna use this Desmos calculator. So what I had previously was this sine of x times pi, like this. And we were going from 0 to 1, so basically that's why it looked like a jump like this. But I wanted to start off like, I don't know exactly what I want. I think I wanted to go down a little bit go up. Like to have a little bit of a warm up before the jump. So if it would start here a little bit lower, I mean closer to 0. Yeah, let's see what happens if I add the cosine. Times or just offset. Yeah, now it's doing something, but I would like to translate it a little bit. So mhm. um, I think the translation should work like this. I want to yeah, this is what I wanted to do. So now I want to position this so that it starts off at 0, goes up like that, and then back to 1 somehow. Something like this. And probably this needs to be squished more now. Now, let's do these separately. No, why did it do that? Yes. Mm-hmm. Yeah, something like this. Okay, so now I'm getting something that I want. This kind of wind up here and then the jump. I think this is something that I can go with. Yeah, let's try it. So here, mm, let me actually go to the math and create our own function here. Mm. Mhm. So the f value is going to be math.sine x times math.pi. G is going to be sine plus t times pi times 2. T is 4.5. And we return f plus g. Okay, so now back to the bird. Yeah, it's still using that function. No, I don't like it at all. It's going below the line, and somehow I thought it's a good idea, but I was thinking about the head going below the line. I mean, the head going like that. Okay, let's keep the sine function there and see if we can use it for the head somehow. Okay. Mm-hmm. I need to do this if to bounce here. I think so. Otherwise, the head value is just going to be that. But if we do the bounce, we modify it once more a little bit. Mm. Okay, it's fine. Let me also add a pause at the end. So if we are doing this bounce, I'm gonna add a few more frames at the end. Like this with the last frame. So I'm gonna give it a little bit of waiting time there. I think this should be negative here. No, it should be positive. Yeah, that's correct. Okay, what happens if we increase this significantly here like that? And if we do it the other way around? Yeah, how about if I make the leg length bigger? Yeah, difficult. This doesn't seem to be exactly what I want. Let me undo some of these values there. So I repeated these at the end so that the character stays a little bit after each jump. Somehow I would like to have this wind up for the jump, but it's not going as I want it to. So when we're moving, I don't want to add, I want to add some frames in the beginning that are like this. Like nothing would happen in them. Except for the head. Yeah, so basically I want to offset here. T and U. I want these things to happen after the wind up. So where we're interpolating here. Difficult. Yeah, basically I want the actual jump to start a little bit after. Okay. Yeah, so if I take this T, make it bigger like this, then subtract this, I'm gonna get some negative values in the beginning. And if I'm gonna write here the maximum between 0 and these negative values, then I'm always gonna get 0 there. So I'm essentially delaying the jump itself a little bit. It's not noticeable, is it? Okay. This should work. So maximum, yeah. Let's go to the bird move to and debug it. Starting to get tired. Okay, yeah, so this is minus minus getting close to the positive. Yeah, let's just subtract the lot from this. And now the legs shouldn't go off the ground at all. So what? Oh, damn, no. This was fine as such. Or actually, no. Hmm. Okay, so W here, W here. I was not controlling here, this one, the vertical part. So yeah, very confusing part here. Okay. Yeah, and this offset here only if the bounds. So if two bounds, then that's otherwise just T. Yeah, that's not very bad. I'm I'm happy with it. Um, Hard to explain what I've been doing just now, but somehow offsetting the frames for the actual jump and allowing the head to go down a little bit, few frames. Yeah, this is fine. So maybe just a little bit. Nah, it's just fine. Let's just play a little bit more with it. Yeah, how about we give the height here lower one. Yeah, this is good. Okay, I spent a lot of time on this, but I'm happy with how it feels. And a little bit difficult to explain what I did because it's a lot of trial and error and yeah. But yeah, I think it's good. So styling the bird next. Do the actual drawing. And now we have here draw and we are drawing the head. So this part is draw head. Let me extract here draw head on the context and call here this draw head on the context. So everything still works the same, but now we can style this a little bit differently. I'm gonna put a stroke. Yeah, and also a fill with a fill style that is white and a stroke style that is black. But I want the bird to be a different color, so maybe, I don't know, let's try orange, red. Something like that. Yeah. So the head is something like that. Now, maybe the radius can be a little bit bigger. See? Yeah, that's good. And let's add some eyes to the bird. So white and let's go to the head x, head y. Head x minus radius times 0.4. I need to begin a new path, I think. And the radius of this one should be just a fraction. Let me define here. Yeah, okay. And then here I size divided by 2, that's the radius. Too small. Something like that. I want also to stroke this with maybe gray stroke style. No, maybe black. And let me move this head over the legs because I get disturbed when I see the legs like that. Okay, bigger eye, and I don't want to use arc, I want to use an ellipse. And the X and the Y, they are just fine. But this is now the X radius. And we need a Y radius as well. Let's make it X radius is this times 0.4 and this is 0.5. And I also want rotation, so math.pi, no, just minus 0.1, I think it's going to be good enough. More, minus 0.2. And let's make this 8. Yeah, this is good. Maybe 0.3. The ellipse is slightly rotated. Yeah, I like it. And here minus 35 maybe. No. 25. Yeah, this is good. So this is the left eye, and let's give it also a fill, a small pupil there, which is the same kind of ellipse, but I'm going to make the radius much smaller. I need to begin a new path. Yeah, that's good. Let's get this closer to the center point and have it look down, plus radius times 0.2. Too much. 0.1. Okay, something like this. And repeat this for the other side. So left eye plus 0.3 the rotation, plus 0.3 the rotation, plus here. We have 2 of them, but this X seems to be too small now, so let's change it to 24. Okay, wait. So the big one here needs to go more, let's say 28. 28. Yeah, 32. Spreading the eyes apart a little bit. Okay. Good. And now let's draw also a beak. Let's just go like this, and this head Y. Yeah, a little bit more. Something like that. So I'm moving there, and line 2, I want it to be exactly at the same center here, but this one bigger, and then another line to this one but with the plus. So I'm drawing a triangle that is somehow oh, it's funny. Yeah, I think it could be even bigger and wider. Let's see what happens if we make it. It's funny. Something like this. So I actually want to move this to happen before the eyes, and I want to still draw it with the red. Yeah, and let's make it bigger. Let's make it 5 and wider also. How about 32 here? This is not bad. But now the head is same color as the beak, and I want the beak to be somehow more visible. So let's change this into a blue color. Something like that. It's fine, I think. Okay, now I could draw some kind of funny things on the top of the head, maybe some feathers going in a funny way, or these um, wings on the side. Yeah, I could definitely do that. I could also animate a little bit the facial expression. So when we're drawing the head now here, drawing this, could get a t value here. 1 minus t value here, but it won't matter, so I'm gonna apply the sign again. So let's just call this t is equal to this q length divided by 40. And actually I'm going to extract this 40 and say make it a global variable, like at the top here, and say how much I want this frame to like the each animation tween length 40. And I'm just going to use this one as a global variable. Not as a global variable, but I'm going to pass it here. Sorry, not there. Where we do the animation and we move to. So here, we move to these, passing this tween length, like the number of frames, basically. And here I have to say false because it's not bouncing. And not great. I don't have access to it here. I don't like this being there. I guess I can pass it here, but it's ugly. Okay, so then does this still work? Okay, and if I change this tween length to something else here, like 140, does it work? Yeah, it seems to work just fine. Okay, but let's keep it 30, a little bit faster. No, too fast. 50. Yeah, okay. And draw those feathers now. No, I was talking about making the animation. So here, draw, when we are drawing the bird. So we get this t value, and then we get u. Like that. And depending on this u, which I'm gonna pass also to the draw head, I'm gonna say eye openness, something like this. It's a percent, so I'm going to change the eyes. The ellipse is y radius plus this. Times eye size times 2, something like this. Let's see if it works on one eye. It getting bigger, but I don't like it. Maybe it should be smaller. And I think it should only happen during the bounce, so no, this is not nice. Not a nice way to animate things. I think all of these could be properties here, but then it's confusing. I'm gonna have to work on this animation method. It's not the best. Yeah, let's just not do this. Yeah, okay. Let's work on the legs a little bit. So how about I write here stroke style blue. Now we have blue legs, line width, let's say 5. Now everything becomes 5. Reset it to 1 afterwards, so now we just have these thick legs. Line join round. So these are now rounded knees there, and also the line cap is probably a good idea to keep around for the tip of the feet there. Yeah, that looks okay. Dark blue maybe? Yeah. How about having some stripes on the feet? Let's make them thicker. Too thick. This is fine. And the stripes here, I don't think we need another begin path. We just continued there by moving to the other leg. And after we stroke, I say ctx set dash style. Let's try with normal blue. And stroke. And then reset the dash style as well. Okay, I think the thickness is too big and I don't see it anymore. 6.6. No. Oh, set line dash. If it's set, then it's probably the name of a function. Okay. Something like that doesn't look bad. Smaller, maybe. But the feet should be also orange. I think so. So dark red, maybe. Orange. Red and orange. Is there brown? Yellow. Not bad. But I think what I will do is set it to black, like this, and give it a bigger stroke. Or maybe not. Yeah, let's set it to black, do this thing, and then after the stroke here, I'm gonna set it to yellow. I'm gonna decrease this size to 4, and I'm gonna stroke again. I think that's gonna give me an outline. Yeah, I like that effect. So I'm getting an outline for the feet now. Yeah, that's good. And here maybe we can do them more tightly packed now. Yeah, this is good. Let's draw the beak also with this yellow and see how it looks like. So now, how about switching them around? Black. Oh, I guess this is fine. Maybe yellow. No, orange is better. Yeah, this is fine. I could draw the feet somehow to look more like a bird's feet. Yeah, let's do that. So, here I'm drawing the foot. And I would like to somehow spread it apart. So, I want to go away from the knee somewhere close to the end. So let me do interpolation here. Like ankle, the ankle location is equal to VLERP from this left knee to this left foot using maybe 0.8. And now from this ankle, I want to I need to know the angle that we have here. Between the knee and the foot. So So this. And let's add now some. To this ankle location, let's get the distance. Like this. And 2 fingers. I should probably extract some function here, but getting tired. This no ankle x plus. Is that how you write ankle? Yes. Okay. Plus distance times math cosine of angle. Essentially, this here is using polar coordinates relative to these angle. I could extract some smarter functions, but plus 0.5 and minus 0.5. And now move to the ankle. And line to this finger 1. Actually, I can do it with 1. I go to the finger 1, then line to ankle, then line to finger 2. I think like this. Let's see what happens. Wow, errors. L foot is not defined. This L foot. Well, something is there. I think this angle is too big. I need to put here. No, angle is good. I think I made a mistake here. Yeah, this is what I'm going for. But here, maybe we put more like... funny. Let's put it to 7. Yeah, and definitely I want to extract this somehow, so... At least this, it's like the minimum I can do at the moment. Always getting tired after eating too much. So, drawing the foot, this dot draw foot on the context using this left knee and this left foot like this, and then draw foot using right foot and right knee, and didn't work. Why didn't it work? Uh-huh. This begin path, I think we need just one of it. Yeah, okay. Nice. Now the socks. I would like the socks to be also a little bit more beautiful. I'm gonna make the bird have some other features also, but so far it's looking good. The socks, okay. I don't think I need this debugging part anymore. Let's still keep it just for. Let's set stroke style also to this color and also do a stroke here. It's gonna make the socks a little bit thicker, especially if I'm gonna set line width to 3. And because I've already made this, let's put 5, because I already put the line cap how it is around before, it's going to affect this as well. So now the socks are a little bit more roundish around the corner, and that's exactly what I was going for actually. Let's see how this changes if I'm gonna have 16 elements. There's a little bit more spacing there, which I like. Let's switch back to 20, and the width of a sock, what happens if we change this one to 8? Maybe we can get away with 18 elements. Yeah, this is nice. And end. Let's now go to the sock here, and CTX line width equals to 1, CTX stroke style equal to RGBA 000 0.3 3, so I'm gonna give it a black with transparency. CTX set line dash 2 and 2. Let's also reset this afterwards. And stroke again. Not bad, maybe a line width of 2. And a line dash of 3 and 3. Maybe transparency 5. Okay, I want it to look a little bit like knitting on the sides. So maybe back to 2 and 2. Somehow this is not very bad. Okay, this is starting to look like something. Somehow I don't like that the sock is hanging on this one tip there. How did these particles get generated here? What happens if I move this current height here at the end? I think this is good. It still has this small triangle there, but yeah, and here where we are generating the numbers, let's try 0.3 so that they are at least a little bit long. So now it looks a little better. And maybe we want some kind of clothespins there. So I'm just gonna go in the sock here where we're drawing it. And after I draw it, I'm going to go put line width to maybe 4, stroke style set to black, and just do a small line from first particle location y minus this plus this. I will probably have to change it, but Ugh. Yes, it's a new path. Yeah, not exactly. It's kind of ugly. Also, these legs somehow blend in between. I don't like it very much. I'm gonna have to do something about that. Draw them individually as separate paths, I think. So here, let me just make this. And like that, so that the pins are a little bit higher up. And I would actually like, how about giving them some okay. And before I draw all of these things, I could draw another one. So now there is a line, one behind and one in front, and I can make the X of the one behind, the bottom X, offset a little bit to the right. So it's a small thing, but I actually made it look like scissored a little bit. Now you can get what I mean. So a little bit, let's try like that, where one of the things is going in the back and the other thing is going in the front, and that transparency somehow adds a little bit of an effect as well. I think that's fine. Yeah, let's add a little color as well. Okay, so now we have also some cloth pins there. Let's fix these legs of the creature. So here where we're drawing the foot, I think I want to draw the foot like this to begin the path and include these things. So stroke, yellow, orange, set line dash. I think this should be. No. This part also needs to be here in the beginning. Yeah, now the other sock is behind. Like the one pushed by this leg should be behind the other one. So I do this. Yeah, this looks great. Mhm. Let's style this bird a little bit more, give it a few more details on the head. So before drawing the beak, I'm going to do some ellipses here. Just copy it here and say, where is it? Okay, it's inside there. So I don't want it like there. I want it on the top of the head. And I want it like this actually. Yeah, something like that, but even more up. Even more up. Okay, not bad. Mhm. Let's try to interpolate something here. So let's try to add to the X something. Okay, let's actually replace this with T and see what happens. Mhm. Mhm. T minus 0.5. Like that. And now this rotation T minus 0.5. 0.5 minus T. I want it to be the opposite. that's getting something. And the Y here. um, Something like that. It's a little funny. Maybe I can extract this as a function. So a method here, draw feathers on the context at the given center. So now this would go here, and the center is going to be this head x minus radius whatever. Mm-hmm. Okay, it still works. So now I would also like to add some angle, and that's what I'm going to add to the rotation here. Hmm. Okay, but how about if I would reuse this on the side somehow? Does it work? I don't think so. So something strange is happening there. I need to use this angle somehow when offsetting it here, I think. Hmm. No, this was good, but the angle here, hmm. Okay, so let's also offset this head. This part is just messy code, me trying to get something that looks good. I don't have good coding structure anymore. Minus radius. Yeah, okay. So now what happens if we repeat this? Mhm. On the left. So it's the same thing here, but also with the angle parameter. So it should be the other way around. Mhm. Mm. Okay. I think my camera is somehow not recording anymore. Got it back on. Getting too tired to do this mental calculation right. I think I'm gonna keep these like so. And I'm just gonna do some tricks that make me able to do this without the mental math. So I'm gonna say save the context, restore the context, and now translate this head X, this head Y, and here I'm just going to draw it 0, 0. Okay. So let's translate that this head Y plus minus radius. So this is going to put them back on the top times 1.3. Yeah. And now Let's do this again and do it on the side like this. Okay, but also rotate. Something like that. So that's kind of what I wanted to do, but doesn't look fantastic, not just yet at least. And let's do it also on the right. So plus this, and then rotate towards the right. Okay, somehow I want to have this same orientation there as on the left. Maybe the feathers should be drawn in a way that it's more symmetrical. So we start off from 0 to 5. Let's just keep here t like so. And not do this trick. Wow. Yeah, something like that, but just go until 3 here. Like that. And then do this. Interesting, I didn't expect this result. Huh. Hmm. Oof. Nope. Maybe I just undo everything and think about some other way. Okay. Yeah, this could be done much nicer, like if the feathers would be also affected by physics. Just not enough energy to do things like that today, and my time is running out. And now I'm not even able to do this drawing properly. Let's try again. Well, it worked somewhat. Okay, now they look symmetric, but those ones on the side, I would like them to be not so wide. So somehow controlling the spread here. Like this, and now we're doing this radius. I don't actually need this angle anymore. It's yeah, it's a constant here, like that. And let's put now this spread just 1/2 here. Wow, not what I expected at all. Okay, so the one on the right is good. Context, center, radius, spread. I think this is what needs to be done. It's a little funny. Yeah, and when we are doing this, we go here also depending on the spread, I think. Yeah, now the ones on the side are not as spread out as the other ones. Not bad. Maybe if these feathers on the side would be below the head. And how about reducing somehow this? Say just 2 for the side and then leave it as before. So less feathers on the side. I think this looks nice. And we could do it with dark blue. And then switch to blue for the head. About the head would be dark blue. Something like that, but back to blue for these feathers on the top. These seem not to affect anymore. I think I'm messing something up. Very weird. Okay, one thing I don't like is in the beginning when we are starting this, it jumps once for no reason. So I think that here in the script I'm just going to after I get the moves, I say that. No, then I just get the first the first move here. That. So, okay. And let's give it a little bit of time in the beginning. before things start to happen. So I'm going to say here yeah, something like ctx start, oh, sorry, constant start time is new date get time, and if new date get time minus start time is greater than 1000 and these other things. So I give it a second in the beginning where it does nothing. So we let those socks settle. This looks great. I like it. I'm not perfectly happy with it, but for a day's work, it's great. I'm curious, could I change the vertical position of the socks? Like where I'm defining the socks here, what would happen if I would give a little bit different value to this, like plus I times 4? Seems to work. So I'm going to give this a little bit of a curve. It's rising the margin. Yeah, and like this, it's nice. Kind of lucky with it. Yeah, so it seems to work just fine. This leg is getting a little bit too stretched. Maybe this is margin times 0.7 or something. Yeah, let's play a little bit more with the bird. So where I'm defining the bird, let's give it this was the part, yeah, and here we were getting the leg. Let's make it a little bit bigger so this effect doesn't happen. Yeah, this is good, I think. And of course I want to draw this line that passes through them somehow. So where I'm drawing the string, this is the string. I think I'm just gonna try to eyeball it. I'm just tired. I want the curve, so CTX. And then I think it's like this, but then I have to specify some control point. Let's see. So in the middle, and then no, it's the opposite. The control point is first, and oh wow, it's not very bad. So I think that here minus margin, minus margin. No, this one's good. Maybe. No. Okay, minus margin, but then this curve is not good enough. I need the Bezier. I mean, cubic Bezier. This is already a Bezier. So let's try here a third of the width for the first control point, and then 2/3 of the width. A fourth of the width and 3/4 of the width. Fifth of the width and 4/5 of the width. Let's go back to 4 here. Yeah, so eyeballing it pretty much, but this is it. Yeah, let's see what happens if I speed this up a little bit. Where do we have that? Tween length, let's set it to 30. It's gonna be funny. Yeah, it's a little faster and it's funny. So now the bird is just going back and forth and back and forth, and I'm done for today. I hope you learned something from this, kind of like in the last video with the avatar. I just become really tired by the end of this, and I stop making much sense. Too much mental calculations and not enough explanations, but I just can't do it all the way, and I didn't want to leave it for the next day like I did the other one. But I'm really happy with this. I was hoping to generate also some sounds for the bird, but no, not anymore. I had enough. So yeah, Let me know what you think and if I should make more videos like this that show the full thought process. Of course, this should be refactored now. Some things here I just don't like. And I think that animation where I'm generating in between frames, I think I should have a designated function for generating those in between frames. Now I have that interpolation, but it doesn't generate them. I generate them in the move to function, but I should have a separate one that just gives me the frames and then do some array manipulation, like mush frames together in a single object. It's hard to explain what I mean, but yeah, I'm thinking about making animation software one of these days. Maybe not in the near future, but I would like to make a tutorial how to make drawing software and animation software, and I will use some better structure for those. Okay, that's it for today, so see you guys.